Good afternoon and welcome to all the participants on the fourth day of STTP on Advances in Civil Engineering. It gives me immense pleasure to welcome Ms. Monica Shah, our expert faculty speaker for today's STTP topic, Computational Fluid Dynamics in Environmental Engineering. Ms. Monica Shah holds BTech in Civil Engineering from MS University, Baroda, and Masters in Environmental Engineering from MS University, Baroda. She joined Navrashna University in 2013. Her field of specialization is in the area of environmental engineering, especially in wastewater treatment, water analysis, industrial effluent analysis, and design. She has taught various courses across civil engineering, such as environmental engineering, fluid mechanics, water resources engineering, geodesy, soil waste management, hydraulic structures, building drawing, research methodology, and several sessions on Coach. She has guided several final year students in the area of pharmaceutical wastewater treatment, dairy wastewater treatment, desalination, Sursagar Lake quality in Ganpati Visarjan, vertical sewage treatment plant, solar e-waste management, contamination of soils, etc. She has published many research papers in peer-reviewed international journals and proceedings of international conferences. Currently, she is pursuing PhD from Navrashna University. I now invite Ms. Monica Shah to deliver the session.
Thank you so much, Saloni ma'am, for the kind words. Good afternoon, all of you present over here. Ma'am, can you see my screen?
Yes, Monica, ma'am, we can see.
So, good afternoon, all. Today, I'm going to present a topic on computational fluid dynamics and how that is going to be relevant in environmental engineering in the fields and the different scopes of the same. The outline of my presentation would include the introduction, that how the environmental engineering is affecting to the world, the treatment options on the environmental diseases, the one of the promising technology for the reduction of the pollutants would be the computational fluid dynamics, how the CFD is going to work, and the applications of computational fluid dynamics in environmental engineering. And after that, I'm going to closure my comments on that. So if we are going to start about the introduction, in that I would say that what would be the major concern in today's world? If we are talking about the major concern, I would rather say that the simplicity and the comfortness for each and everything would be the major motto of every person on the planet. The scientists are going to produce new and new inventions on each and every field, and that makes our life very easy and convenient. For example, if we would love to say that we have the one who has seen the transition from landline phone to the mobile phones and mobile phone to the smartphones, even from the basic computers to the desktops, to the slim desktops, to the laptops, and now the many much more invention is going on that particular field. Likewise, there are so many inventions and so many industries are going to be established within a year. As rightly said, nothing is free in this particular world. Every time we have to pay something for anything, right? The same way, our world or the nature is so generous to us when they are giving all the things free of cost. But at the same time, when we are developing the things on the nature, we have made so many much amount of pollution on this particular world. And if we are talking about that pollution, that would be included water pollution, air pollution, soil pollution, land pollution, right? And many much more type of the nuclears and the radiations and so much going on. In this particular figure, if you could see how the comfort life or how the comfortness we want, that should be seen on the greener side, and how the things actually are, that would be on the right hand side where we are actually living in. Let's talk about the basic about the pollutions, how the pollutions are getting generated and treated. First, we are going to discuss about the water pollution. If we are talking about water pollution in this particular first figure, you could say that so much amount of solid waste and other impurities are thrown. As these impurities are thrown on the surface of the water, there is no flow in this particular water. Even we could say that there should not be any kind of biological activities are going to be present in this. As a result, this kind of lakes are going to be dead within a few years. The aquatic life, the vegetation growth, the complete flow of water that could be the source of water for us, let's say, right? The surface water, that would be the major source of water that we have. So if we are going to see this kind of scenario on the planet, the second figure shows that the industrial effluent is getting mixed with the surface water sources, not by the quality, but just by the visible things or the color which is going to be mixed in this particular figure. We could say that this gray water is going to increase the tremendous amount of impurities in the water, right? In the third figure, if you could see the green water, there is nothing like a green color water on the planet, right? As we know that water is the one substance which is colorless. When this green color water comes from, this green color water is the algal growth on the top surface, and that algal growth is going to stop photosynthesis process beneath the water surface, and they are consuming the dissolved oxygen from the water. As a result, the process of eutrophication is going to be held, and because of that, this particular water source is going to be dead in a few years. In such crisis where we could say that we don't have enough amount of resources, rainwater is the only source of water, and at the same time we are doing this kind of activities in the water, that leads to the shortage of water. As an outcome of that, we need to go for the proper wastewater treatment. If we are talking about the wastewater treatment, the basic treatments would be divided in the three basic parts: primary treatment, secondary treatment, and tertiary treatment. Why we are giving this particular treatments? These particular treatments are given to the sewage which is generated from the household activities, as well as to the industrial effluent which is generated after the manufacturing process. In that sewage treatment and industrial effluent, we never mix them. They both are getting treated separately because the composition of the wastewater in case of sewage as well as industrial wastewater are totally different. Even if we are going to say about the industrial wastewater treatment, then the quality of wastewater is getting changed by each and every industry. If you are going to change the manufacturing process, if you are going to change some raw material in the process, at each and every time we could find that the quality of the wastewater is getting changed. So generally, the basically first will apply the primary treatment to that water. That primary treatment is going to remove the visible particles which are on the higher size are getting removed. The first process in that particular case, that would be the screens. Generally, the screens would be the core screen, or fine screens. If you have a sewage wastewater, we'll go for the coarser screen. And if we have an industrial wastewater, we'll go for a finer screen. As industrial wastewater doesn't contain a bigger or sizable amount of impurities. So in that particular case, the bigger particles are going to stuck over here on the screen, and the rest of the water is going to be moved in this particular chamber. After that, if you found that the particle which are this in a bigger size but they can pass through the gaps between the screens, in if you want to remove them, what we'll do, will provide the communicators. These communicators will break the each and every component of this particular particles in a smaller size so that they could be easily settleable. After that, it is going to be settled in the Great chamber. Great chamber is the one session where the heavier impurities should be settled out, but definitely not the organic one, as the organic impurities are required in our secondary treatment. So the main and important task while we are designing the Great chamber is to set the velocity of the Great chamber. We have to set the velocity in such a way that smaller particles can remove, smaller particles should move ahead in the secondary treatment, whereas the inorganic and the heavy particles should be settled down in the Great chamber. After the Great chamber, generally the velocity is going to be suddenly reduced in case of a clarifier. While we are providing the primary clarifier, the particles are going to settle down. Here, the suspended and colloidal impurities are getting settled. Sometimes between the Great chamber and the primary clarifier, the velocity control devices like a partial flume or something like that, or vias, they are going to provide so that flow is going to be diverted or the velocity of that particular thing would be reduced, because we need to slow down that velocity, because in primary clarifier we have to give a proper detention time to that particles so that they can easily settle out in between in beneath the tank. Sometimes to increase this particular process, to speed up this particular process, we are going to add the coagulants, and that after the coagulation and flocculation process, the flocks are getting settled in the provided primary clarifier. After this, the effluent, which is going to be move ahead in the aeration tank, which is to be considered as a secondary treatment, or sometimes it is considered as a biological treatment. There are different types of biological treatments available. The general and versatile biological treatment would be the activated sludge process, and here is that provided as an aeration tank. In this aeration tank, we are providing the excess air through the air compressor so that the amount of dissolved oxygen would be maintained in this, and the microorganisms can grow very easily in this particular tank. The effluent which is coming from the primary clarifier, they will enter into the sedimentation, aeration tank, and in this aeration tank, they are started consuming the organic matter which are present over here. The bacteria which are available, they are decomposing it and converted them into the simplest form, and that are going to be considered, or they are going to be sent to the secondary clarifier. In this secondary clarifier, the bioflocks which are generated, they are going to settle down. After that settling down, the other water is going to be recycled, which is the active sludge, and the rest of the clearer water is going to be as the next procedure. After the secondary clarifier, if you could see that still some amount of impurities are present, or some other objectionable things are available, in that case we have to go for the tertiary treatment based on the impurities are available. Otherwise, the simple disinfection would prove to be a very prominent thing to discharge them into the surface water. As we could discharge them into the surface water, it should be something in that particular state where it should not harm to the aquatic life which is present over there in the surface water. As we have discussed about the water pollution, the similar kind of air pollution is also available in the atmosphere. You could see in this first figure that amount of smoke which is generated on the atmosphere. In this particular figure, you will find the person who is standing over here is getting breathed by the only polluted air because she is surrounded by it, right? This is the current scenario of so many cities in India even, right? Delhi is one of them. So in this particular, in this regards, if you could see that there is no breathable space even, that kind of cities have already started using the mask before even pandemic just to save themselves from this heavier pollutants. This kind of pollutants which you could see, they are going to be classified into the different categories. If the source of pollutant is stable at one place, then it would be considered as a stationary source. You could consider that as a chimneys from the industries, or we could consider that as a power plant, thermal power plants, or a sewage treatment plant, the gases which are generated over there. That kind of source where the source is not in a moving condition, will consider them as a stationary source of pollutants. The other are mobile source of pollutions, just like the vehicular emissions and the aerospace pollution which is generated. Such kind of sources are considered to be as a mobile source. Some kind of sources are the a source of pollution are the naturally occurred, just like volcanic eruptions or a forest fire or something like that, or sometimes even a lightning. Such kind of things are going to be as a natural one, whereas the man-made we already know are about the industries and vehicular emissions. Such kind of pollutants, if we breathe in our human body, that is going to be very risky. There are some diseases like asthma. Sometimes it leads to the cardiac arrest even. We'll go for eye irritations or skin irritations and itching. Such kind of diseases are going to be there. So as a solution of this, we need to provide devices which can control the air pollutants. Now, basically, the air pollutants are divided into the two categories. The first category is to be considered as the particulate matter, and the second one will be the gases. Let's start with the particulate matter, right? So, the particulate matter, they are available in the air. They are in the floating conditions, right? Because the density of that particle is very less. So as a result of that, they can't be captured very easily. So we have to set up the device through which, if we are going to pass through that particular particulate matter or a gas or a air, in that case, such kind of heavier or a lighter particles are going to be captured very easily. There are few devices are already available in the market. The very first and very old one is the gravitational settlers. In this gravitational settlers, you could see that the raw gas or air is going to be entered into the unit. Over here, it is going to be entered with pressure so that the heavier particles are going to be settled in this collection hopper, and the clean gas is going to be moved out. Very easy to install, very handy to use, but the limitation is that the efficiency of the collection of the particles is very less. Generally, the particle size which are greater than 50 micron meter, only up to that kind of particles are getting captured and settled over here in the gravitational settlers. So to improve that efficiency, the another device which is used is the cyclone. Cyclonic thing is work on the centrifugal force, where you could see that dusty air is getting entered into the system and the heavy centrifugal force is going to be applied. Because of this centrifugal force, the particles are going to be stuck, or they are going to be thrown away to this particular walls, and then they are going to be captured in this particular dust outlet, and the clean air can be moved out. Such kind of devices are so easy to use and handle, that you could see that in this particular image there is a truck behind this, and in this particular truck such a small cyclone is provided, so that the you could say that the impurities are generated and they are captured at the same point. So there is no source of adding the pollution into the atmosphere. Before that, they are going to be captured out. The another device for the particulate matter would be the wet scrubbers. In this kind of scrubbers, what they are going to do, they are mixing the particulate matter with water, and then they are going to be clean it with water, and you have to remove that impurities from the water itself. So you could say that it is just a conversion of gaseous pollutants to the water pollutants. So the contaminated gas is going to be entered into this, and the water spray nozzles are available over here. The water is going to be sprinkled easily over here. The water is going to be entered from this particular pipe. They are getting mixed with this particular packing, and the clean gas can be out, and the contaminated water and gas is going to be mixed with this. Though this kind of method is required in certain cases, the because it has a advantage of getting a very small size of particles are even captured by this. Less than 10 micron meter particles are even captured in this kind of wet scrubbers. So in certain places, this kind of things are going to be used. Generally, on the places where you have a proper or enough amount of water treatment systems available with you, you can go with the wet scrubbers. After that, we'll have another one, that is the electrostatic precipitator. This is the very uh, handy, and you could say a very effective machines generally used nowadays in all the industries to remove the particulate matter from the atmosphere. Even it can capture certain amount of smoke particles too, right? So what is the thing over here, that the gas is going to be entered from this, and over here you could see this particular net, where this net is the negatively charged metal particles. So when the gas is passing through this, they are getting the negative charged, and after that the positively charged plates are collected over here. So this negative positive charged are getting combined to each other, and they are attracted to this particular plates, and then you could remove that particulate matter, and the clean gas can be removed from the other side. So generally electrostatic precipitator, generally commonly known as ESP, is used to remove the particulate matter from the atmosphere. So
Saloni ma'am,
Yes, sir. Yes, sir. I'm
just
inside here.
yeah, yeah. I'm making you host now.
Yes, yes. Thank you, sir.
You are the host now, ma'am. Continue.
Okay. Thank you. Thank you, sir. Thank you so much. We are very sorry, participants, for the interruption. Yes, Monica, ma'am.
Yes, ma'am.
Yes, please continue.
Okay. So, as I have discussed, that electrostatic precipitator would be the best and prominent solutions for the in case of a smallest particulate matter that would be the less than 1 micron. So other control devices which we could see, that is for the gaseous contamination. And for the gaseous contamination, generally the adsorption and the absorptions are the techniques which are going to be used. Just a second. Okay, so what is adsorption? Adsorption is the passing a gas through a one porous solid material, and in that solid materials, they are the particles are going to be attract, and they are holding the gas. Now, this procedure is going to be carried out by the physical or sometimes chemical adsorptions. So, the common adsorbents which we are going to use based on that, the gaseous contaminants are getting attracted to that. If we are talking about that, the first one will take as the activated carbon. So that activated carbon is the one which is used to eliminate the color and purifying the gases. Another one is the butexite that would be treating the petroleum fractions and the drying gases. The bone char is going to be used for decolorizing the sugar solutions. The decolorizing carbons are going to be used to decolorizing the fat, sugars, and the domestic water. Other molecular sieves is going to be used for controlling and recovering the SOx and NOx emissions, and silica gel will be the drying and the purifying process. Other absorbents are there. I have listed a few ones over here. Another procedure which is going to be used is known as the absorption. So that one would be the one which is on which there is going to be hold here, it is going to mix with some material, right? So what is going to be done, that it is going to bring the contaminated effluent gas in contact with some liquid absorbent, and that is known as a solvent. So it is going to mix, and they are going to constitute one more effluent out of that, and from which the gas is going to be removed, treated, and modified based on the liquid absorbent which we have used. They are also going to be carried out by the physical method or some chemical changes to remove this kind of pollutants. This is about the gaseous things, that from the gases we could remove the other different noxious gases. If we are talking about the land pollution, in that particular case, we could see that in this image, you could see that there are tremendous amount of solid waste which is dumped, right? And the besides of that, we could see some rivers, the side of river, that would be something like a power plant is visible. So if you are living in such an polluted area, you cannot breathe a proper air, you cannot have a proper food or a water, because everything over here is polluted. You could see that the tremendous amount of plastic waste, the garbage, and everything is going to be dumped every time, every day. If every people is creating such kind of nuisance on the land, in that case we don't have enough space to dump this kind of the arrangements. So in that case, if we don't have a proper amount of disposal space, then where we are going to dump it? If you are going to imagine a situation that if the person who is collecting the waste at your place is not going to be present just for a week, you can imagine the situation, that amount of waste which is generated at your place. So if this is the scenario, in that case, how we are going to manage the waste of the whole city? We have to go for the motto of 3 R's: reduce, recycle, and reuse. For the treatment options in case of the land pollution, we have different options. From the collection itself, we can reduce, right? Or we could even generate the less waste in terms of solid waste. If we are talking about right now, if we could generate less waste, then we could definitely reduce the waste, right? After that, generation of the waste at the source of itself, we could segregate it properly, then that would lead to a better place for the disposal. As you could see in this particular figure, just a second. As you could see in this particular figure, where we have segregate the paper waste, glass waste, plastic waste, and metal waste. So what is the benefit of segregating the waste at the source? Of course, even our government has started collecting the dry waste and wet waste separately, right? So in this particular waste, there are a content of waste which are organic in nature, and there are the content which are inorganic in nature. If you have the organic waste, that could be easily decomposed and they could be used as a different purposes, as a manure, of course, itself, right? If you have a such kind of glassous materials which are in a reuse, then people are, they are selling this particular thing into the glass factories. They are crushed it, crumbled it, crushed it properly, and then they are again using the same glass powder to mold the another glasses vessels. Similarly, for the plastic, as the government has banned the plastics which are having the thickness less than 20 micron meters, but the things which are heavier than that, they can be easily recyclable, just like our shampoo bottles or there are so many plastic tins are available, the tiffin boxes which we are using. There are so many materials are there. If they have a proper thickness, we could even recycle them. The metal materials, the circuits, what we have, suppose you have thrown the laptops, your computers, your another things which are made up of metal, they are just open it, they are removing all the parts from that particular circuit, they are throwing to the different categories and they are selling it. So this is the way. If they are, if you are removing the copper content from that, if you are going to remove the plastic content of that, if you are going to remove the aluminum parts of that particular circuit, and if you could easily resell it to the consumers who are going to make the such kind of items, then your problem is sorted. Where we need the question is where to throw the waste. There is no question out of that, right? But still we don't have such kind of systems in our country right now. After that, collection of the waste, the major part is the transportation, where and how we are going to transport this to the disposal point. So in that disposal point also we could have different options, like if we have a organic waste and then we are going to dump it together at a single places, then we could even decompose it very easily and make the manures out of that. The gases which are generated could be used as a biogases, right? So there is no question of disposal of solid waste on the planet, where we know that the scenario is very different, right? After this, our aim is to go for a zero waste. As I have discussed that we should recycle the organic waste, we have to reuse the inorganic waste and stop using the non-reusable plastic waste, so that the people have found already so much alternatives for the same. And if we could use them, we could definitely help the environment. Because if we are not going to protect the nature, definitely nature is not going to help us anymore, right? So, what would be the responsibility of the governing bodies? Which are the governing bodies, rather, if we could discuss that the Gujarat Pollution Control Board, as we are here in Gujarat, and above that would be the Central Pollution Control Board, that is CPCB, that is above the state governments. This government governing bodies are going to save this natural resources. How they are going to save this natural resources? They are going to constantly monitoring all this particular industries. Suppose I'm talking about the Vadodara city, then Vadodara is going to be surrounded by so many industries, right? In each and every side, we have on another side, it's the GIDC. This particular side, we have Nandeswari GIDC or IPCL, IOCL, refineries. There are so many GSFC. There are so many industries out there. Here in this particular direction, we have a Gorva GIDC. So we are surrounded by all this industry, and this governing bodies are going to check and monitoring the treatment is going on this particular industrial plant. So what they are doing, they are constantly and on regular basis, they are collecting the samples from that industries, the effluent samples of that industries, which they are planning to throw into the rivers, right? So they are checking it, whether that would be in the permissible limit or not. The limits are already suggested by this government bodies only, that the pollutants, if they are in terms of biological oxygen demand or chemical oxygen demand, now it's an era of total organic chemistry, right? The TOC. In that case, the dissolved oxygen, suspended solids, the nitrates, phosphates, every parameter will be the within a permissible limit or not. If they found that some irregularities are there in the samples, they are authorized to penalize them. Even they can cancel their licenses for running that industries, right? So what would be the outcome? Would be the clean air, clean water, and the clean land. So if the government is working and they are giving them efforts, what is our role? Our role is to follow the rules and regulations which are decided by the government bodies. We have to apply the proper treatment on the generated waste, whether that could be a liquid waste, whether that could be a air pollution, whether that would be the solid waste. We have to apply the proper treatment based on the source or the quality of the waste. And we have to maintain the plant regularly. The pumping systems, the pumping units, and everything we have to maintain regularly. So what do you say, guys? Is it too tough on us? If I'll say, yeah, it is tough, because when we are running the treatment plant at that particular time, it is not something that, once a day we have generated the plant, and then we have the flow, and we know this kind of chemicals we have to enter, we have to add it, they are going to do their own procedures, and our job is done. Is that so? Big no. Because the quality of water or a wastewater which is coming to that particular plants are always different. See, the industries are not going to manufacture the same product throughout the year. They are not going to change, or they are going to change the raw materials. They can change their some products. They can even change few parameters to get the better output. Whenever they are going to change anything out of that, at the same time, your treatments are going to be changed, because the quality, the quantity of chemicals that you are adding, the treatment what you have given may not optimize to that technique, right? So what we have to do, we have to do this procedure regularly basis, that we have to collect the sample, we have to try it whether this particular chemical or a dose is perfect for this particular sample or not. We have to do this procedure again and again on a daily basis, rather than giving the treatment, we are setting the treatment for the same sample again and again, right? That will definitely too much time consuming. Of course, when we are trying different things, the cost is also going to be increased, right? And the factors they are going to affect your treatment. Let's say some treatment is work under some pressure. Some treatment will work most efficiently at under certain temperature only, right? Some procedures are going to be carried out in certain environment only. So such kind of influencing parameters also we have to make sure that would be within a limit. So all those comes together, and that makes our job very, very, very tough. And when we are failed to perform our jobs, we are not be able to apply the proper treatment on wastewater, that means we are not following the rules and regulations. That means the things which should be done smooth, it's not gonna be done, right? So what should be the alternative approach for this? Because we cannot go for every time testing and testing and testing for a daily once or daily twice a sample when the sample is going to change. Sometimes the different batches are available in the industries. The morning batch is different, evening batch is different, night batch is different. So and then 3 times a day, you cannot always go for setting the dose and setting the equations. And no, it's not possible. So what we have to do, we have to go for alternate option. As we know that necessity is the mother of all the inventions, we are also planning to switch to the computational simulations, where the computational simulations can reduce our efforts and the cost. And at the same time, if we are leaving from something, we could improve ourselves from something else. So one of the promising solutions for the same will be the computational fluid dynamics. We all are we all are aware about the fluid dynamics, right? How the fluid dynamics are going to be computationally used over the different problems that we have just discussed, that is going to be seen in the further slides in the computational fluid dynamics. If you could compare the experimental analysis and the CFD simulations, that is would be something like this. When we are going for experimental analysis for setting up the things, let's say for dosing of the chemicals, in that case we could go for limited number of variables. I cannot go for set all the parameters together. Let's say I'll set the temperature complete fixed, pressure fixed, confined area, and then I'm going to add one chemical. At that time the second chemical would be on hold, something like that, right? I cannot go for all the numbers of variables in a same time. So in that case, experimental analysis have that lacuna, where the computational simulations would help when the large number of variables are going to be applied at the same time. The experimental analysis before starting up the plant, we have to try it on the scaled models, right? Where we know that scale models itself having their its own limitations, right? When the scale models are getting in the largest amount, and that time the sum of the parameters or the efficiencies are definitely imbalances, where the CFD simulations will allow the full scale predictions at the same time. If we are talking about the geometry, that if I have made a scaled model, and that scale models, once I have made, I have started experimenting on them, and then I found that if I'll make some changes in diameter or a length, that would not work. So instead of that, if we'll go for a CFD simulations, then geometry will be in our hand, right? If you can change the any parameters whenever you want to change it, and that would work very smoothly with the flow. In experimental analysis, we'll say that realistic conditions are not always possible. Let's say some things are going to be possible only with the temperature at 17-degree temperature. Now, in my laboratory, it's not possible always to create the 17 degree of temperature. It was just an example, right? Similar things I could be implement, or it is in my control, where I have to apply the realistic conditions in the simulation part. The experimental analysis, when we'll go for trial and error for running the plants and all, that would be very expensive as well as time consuming. Whereas the CFD simulations would be relatively cheap and the lesser time consuming. So how the CFD, that is computational fluid dynamics, was invented. This was not the thing which is meant to be only for the environmental engineering, right? The previously that was started or developed under the provision or under the use for the aircraft design. While the aircraft is going to be generated, or they are going to make it, construct it, they are going to go for number of experiments on the wind tunnel. How the wind tunnel is look like? Wind tunnel is something like a long tunnel where at the one side the fan is provided, and on other side the plane model, of course a scale model, the scaled plane model is put over here. After that the fan starts blowing after certain kilometers, and how that wind or air is going to be affected on this plane, that is going to be noted. Now, how to note that? For that, they are going to put the sensors over here on this particular planes. And that sensors will sense what will be the pressure, what will be the drag, what will be the lift, what will be the velocity of the wind over here, how your the stress is going to be felt by this particular plane, and all that parameters are going to be set by the sensors which are provided over here on the planes, right? As I said, it is a scaled model, and if you are going to make the scaled plane model over here, that would be definitely too expensive. They are even trying the same phenomenon with the help of smoke also. So in case of a bad weather or a smoky weather, how the plane or the aircraft is going to behave, that is also going to be tested out. Such wind tunnel testing is too much time consuming, too much costly, and at the same time, these values are definitely on a scaled model, right? So scientists have generated the one, the they are ultimately learning or behaving the fluid which is around this plane. So this dynamic fluid, they have make it in a computational manner and named as computational fluid dynamics, which is going to be used for the aircraft designing. After the aircraft designing, the this kind of phenomenon is going to be entered, of course, into the missile design, car design, ship design, even the blood flow, which is moving through the arteries in your body. We could feel that, oh, that is also a fluid. Yes, fluid is everywhere, right? We are surrounded by the fluids because fluid is not only the liquid but as well as the gaseous components. So the blood flow which is moving through the arteries, at which point and at to which pressure it is going to go for a cardiac arrest, such kind of analysis also going to be carried out by the computational fluid dynamics. We know that the oceans where the ships are going to be loaded, unloaded, and they're transporting the goods from one place to other, at that time the too much amount of oil is getting spilled. That oil is going to be spilled and they are going to mix with the water, sea water. How they are going to react, as a sea water has the salty content, then the aquatic life, how they are going to disperse into the water, such kind of marine pollutions are also going to be analyzed with the computational fluid dynamics. Definitely hydraulic machines are there, we know about the boilers and all, mass and heat transfer flow, where the at which heat and temperature the boilers should work very efficiently before the cracking or a blasting version, right? Such kind of analysis can be done by the computational fluid dynamics. Now, recently people have entered this particular applications into the environmental engineering. Before starting that, let's discuss something around related to fluid dynamics. Uh, Fluid which is in motion would be considered as fluid in dynamic condition, right? When fluid is in dynamic condition, there are so many pressure forces are applied on that body. Suppose I am sitting over here, but at this particular position also, the fluid is passing around my body and it is moving there. Similarly with you, right? This fluid is exist everywhere. We are interested in cricket matches, right? We see the India Sri Lanka series is going on. In that particular one, when your bowler is going to spin the ball and that ball reaches to the batsman. Between that, the ball is moving under the fluid. That analysis is going to be done by the computational fluid dynamics. Even you could see some graphs, in between the overs, they'll show the average of graphs. They are showing that how your ball is reacting, how your ball is moving within this fluid. They are showing you the speed and directions, but that is computational fluid dynamics when your solid body is moving around the fluid, right? In this particular cases, well, we are computationally finding that our complexity can be increased when your flow is converts from steady to unsteady flow. Steady flow, that means we'll consider that the fluid properties are not going to change with respect to time. Whereas in actual conditions, if we are talking about a river, and the river, it starts from point A and it is going to reach points B in few kilometers, then sorry, it's not possible that will have a steady flow up to A point to B point. It's not possible, right? So in such cases, the unsteady flow is to be considered while we are going for the computational analysis. Same as will have complexity can be increased by considering them laminar to turbulent flow. Laminar flow is the one when the streamlines or the flow is moving in a very slow, smooth, and the streamlined manner, where the velocity is very less. And that conditions only your Reynolds number would be low, and that is considered to be as a laminar flow. But in general, if you could see the any water which is flowing in the rivers or somewhere, the flow would be generally the turbulent one, right? So your complexity is going to be increased and your flow is going to be converted from laminar to turbulent flow. The basic three equations, the fundamental equations of conservation of mass, that is, your mass is neither created nor be destroyed. It is just going to change the form from one phase to another. That is our continuity equation. The conservation of energy, that energy is also not going to be destroyed. It is just going to be stored in one form to another form. That is our Bernoulli's equation. And the third one is the conservation of momentum, where the motion within a confined manner is going to become the constant, right? When we are using this particular three fundamental laws of fluid dynamics and we are implementing with the steady and steady or laminar turbulent conditions in the computational manner, we leads us to the modeling, right? Now, what is modeling? That under the world, any physical problem, if you are going to take, and that physical problem, if you are going to convert them into the mathematical model, and that mathematical model has advantageous conditions, and that will give you the proper solutions. Of course, we have to add the control variables or the assumptions, right? Control variables means the actual field variables which is available, right? Because sometimes when we are applying this control variables or in mathematical or a computational language which is considered as a boundary conditions, they are going to be different for based on the different locations and based on different places. I hope I'm clearing. If you have any doubts, you can stop me anywhere, anytime. So if we want to model that fluid flow, we could use the computational fluid dynamics. Now, what is computational fluid dynamics? If we are talking about computational fluid, how it is going to be work, it's not a rocket science. It is just a solution of partial differential equations, that differential equations which are representing the fluid flow, right? And if you are going to solve that partial differential equation and you will reach up to the end point, that would be the thing what is required by you, right? That means your desired output. The phenomenon which we have discussed just now in aeronautical engineering or in missile designs, in a car's designs, in blood flow arteries, or in the, you could say, the heat transfers in the boilers, generally all this kind of equations getting solved by the one and only famous Navier-Stokes equations. What is this Navier-Stokes equations now? Navier-Stokes equations, you could say, are the fundamental equations, and they are mathematical statement of conservation of mass, momentum, and energy, right? The combining these three effects in one equation will make you the Navier-Stokes equation. It is a major invention when the fluid dynamics works very efficiently in the era. Now the question is how this partial differential equations are getting solved. As we have discussed, that computational fluid dynamics is the one which is going to the solution of your partial differential equations. These partial differential equations are based on the fluid, right? And they are going to solve it. Now the question is how to solve that equations. There are basic three methods through which generally almost all the equations are being able to solve. The first one is finite difference method, finite volume method, and finite element method. We'll discuss them in brief from the next slide. The very first method is the finite difference method. Now, finite difference method is basically discretizing the whole structure. Discretizing, that means they are going to cut it and converting them into the smaller parts. The gap between the parts would be the equal. Suppose if you could see this particular figure where this is the point where I am here and I want to find the next point. Let's say मैं अगर आपको ये बताऊं कि this is my river. I am at the point A and this is my point B. I am considering this river as a rectangular element over here. Then my river water will pass from this A point to B point in this particular direction, right? While this liquid or a fluid is moving from A point to B point, it is going to change its property. Suppose मैं find कर रही हूँ velocity. Let's say I'm finding velocity V. Then my velocity is going to change at each and every part of this particular segment. So if I want to know the variations of velocity at each and every point in this kind of situations, I have to go with the finite difference method. This is the condition, or this is the place where I am available, that is in horizontal direction I and in vertical direction J. If I am moving from this part to this part, so let's say this part to this part, so that would be I plus 1. I'm not moving in the Y direction, that is the I plus 1 J. If I am moving in this direction, that is only in Y direction, but not in X, then if that means it's I and the J plus 1th element. So what I am doing, I am completely dividing this my whole systems into number of small parts, which is called as an element. Each part is called the element, and that element is to be found by this particular finite difference method. If you are going to find through the finite difference method, generally the Taylor series expansions will be the use to find the value in the next iterations or in the next segment. This complete portion, which is generally looks like square things, is just considered as a grid. Such kind of solutions are very effective when you have a regular geometry. As I have drawn over here, the rectangular one. If you have a square or a complete normal shape, when you have it, then the finite difference will be the most promising technology to find the answers. Generally, the solution of this partial differential equation will be expanded to the Taylor series expansions. But as I have said, it is used for the regular geometries when I have a something, a screw I have, or I'll have a curvature on the bodies, and in such cases, big no for the finite difference method. Such kind of things can be eliminated by finite volume method. And this finite volume methods, they are going to transform and integrate that particular partial differential equation into the balanced equation over that particular element. So in this case, they are working based on element. The equation will be solved based on the element wise. In the previous method, that was found by the nodes, like the single points, they are going to find it. Whereas here, it is found based on the element. In this element, when you are going to find it for the integral sense, in that particular conditions, this will be the prominent solution method. Generally, the commercial softwares are going to solve the fluid problems based on the finite volume method. The next method, which we could say, is about the finite element method. This is the simplest, or you could say the most efficient method, because it doesn't have any kind of boundaries that it is cannot be used for such kind of shapes or such kind of things. It can be used for any geometry. It can make the things very simple manner. How it works, that I'll show you in the next slide. But the error which is going to be created while using the differential equations or the partial differential equations to the normal algebraic equation, the errors which are going to be generated, they are very minimum in case of finite element method. So the commercial softwares which are working on a multiphysics phenomenon where that more than two things or more than 2 to 3 things are going to be done simultaneously, in such kind of softwares, the finite element methods are going to be used for solving the partial differential equations to the algebraic equations. Now, after algebraic equations, we have the number of methods available, right? The Gauss-Jordan method or Gauss elimination method. We could use any sort of method to solve the equations. So why finite element will be the most convincing method? As I have said, there is no restrictions on geometry. The higher order elements are easy to implement. The mixed formulations are going to be possible in case of multiphysics problems. As I have said, when we have a number of things going to be done in a simple manner, right? The fluid structure interactions, the chemical formulations, and the physical tanks or something. The error which are going to be generated, that can be minimized by selecting the number of elements. If you have a finer mesh, higher will be the efficiency. And if you have a higher order of interpolation function, that the efficiency can be improved, right? Of course, the numerical error will be there. That is the round of error. Sometimes we are not taking the full points after the digit, and that would make the things little bit converged. So there are problems where we have a boundary conditions. That means the atmospheric conditions we have to implement. The walls are, suppose my liquid is flowing through the pipeline, right? Agar pipeline flow hai, in that case, I have to select the boundary layer effect, right? In that boundary layer effect, I have to put the velocities would be 0 at the boundaries. That would be my boundary conditions. I have to put it. That is the rule. We have studied the boundary layer theories, right? So in generally, this kind of boundary value problems, and where sometimes I have a problems where initial conditions I have to give, let's say at time t equals to 0. Let's say my COD will be this, and at time t of 2 seconds or 4 seconds, and subsequently how the values are, the things are going to be changed. That would be considered as an initial value problem. So how this FEM is going to work? This is the simple geometry. If I'm going to crack it, it is going to be in the number of elements, and the beautiful output could be seen. Now this output is nothing like a magic. We love to see this kind of outputs on the figures, but they are not anything like a magic, right? The differential equations are that which are generally not available for the complex geometries. Okay, in that case, what we have to do, we have to divide the domain into the number of parts, and then we have to solve the equation for each domain, and then we have to assemble it again to solve the problem. Generally, when we are taking the equation, which is going to be hold true at each and every point in the domain, but it is not going to be possible, right? It's not going to be correct in the whole domain. So what we are doing, we are taking in the integral sense of that, and that we are going to convert them from the in the weak form of equation. So generally, this is the thing what we have done. That suppose this is the plate where what we are dividing into the number of elements. Each square is considered as element, and each corner points over here is considered as a node. After that, we have to solve our equation at each and every element, and then we have to assemble it together. And if we are finding the values at each and every element, we could see them with the different colors that we have already decided by the codes. This was just an example how the FEM is going to work. It's a partial differential equation, which is going to be exactly true if applying the boundary conditions, and it is going to be exactly true solutions, right? If this is the solution, and then we know that it is not possible in case of the whole integral part. अगर हम लोग एक ही domain की बात करते हैं, then it is true. But when we are going to find it, or we are going to divide into the number of domains, and if we assume that, or if we want that it is going to be true for each and every element, it's not possible. There are error in that. Suppose I'm assuming that this is my approximate solution, then there is some error in this. This is not gonna be zero. There is some error in this. So if I have to solve this equation, then my aim is that my error would be minimized. So if it is error going to be tends to zero, then I can easily solve the equation for the different conditions. So in that case, generally people used to apply the weighted residual method, where we are integrating by parts and make the equation in the weak form. And the weak form equation is getting solved at each and every element. Now, this equation looks so tough, right? I am unable to understand how I'm going to find this velocity u over here. So to solve it in a manner where I don't have anything on my hand to solve as a function, we'll divide them into the 4 different places, which is considered to be as a nodes, right? And when we are considering them as nodes, we'll have a magic equations, which is known as the shape functions. This shape functions will shows, we are assuming that the shape functions are linear, or they are quadratically variating on the other element that we are assuming beforehand. And after that, if we are going to use the same equation, n1 u1 n2 u2 plus n3 u3 u4, that will give me the values of u n1 n2 n3 and n4 and u1 u2, right? If I'm going to make this in a matrix form, and if I'm going to make it together, I'm assembled it together, where my u is unknown, my k is the matrix which is generated from here, and these are the given values, then this would be considered as my global elemental stiffness matrix. If I'm going to convert or combine all this elemental matrix together, it is going to make the global stiffness matrix. After that, just I have to apply the few boundary conditions, and I'm able to solve my problem very easily like this. Now, our computational fluid dynamics is exactly working like this, because it is also a partial differential equation. As you have said, this is also a partial differential equation, but this is a Poisson's equation, where we are interested in solving the Navier-Stokes equation, right? Generally, the shape functions, which is, I have said, it is assumed over the field variables, and the variations, if you have a two-noded, that means only two nodes are there on a bar, then it is going to be vary like this. If you have three noded element, then it is going to be varied like this. So if you want a better efficiency, suppose आपके पास ऐसा एक element है, if you need a better efficiency, just select not only the 4 nodes, you can go for mid nodes also, so that your equation is going to become quadratic in this manner. That is the place where we call in technical term that is primary variables, or it is known as degree of freedom. That would be the primary variables. In case of our computational fluid dynamics, that would be the pressure and velocity. In structural and dynamics, you could say the translation, rotation, stress, temperature, flux. We knew for COD, BOD, anything you could be fine. These are the primary variables. That primary variables are basically based on the type of differential equation what you have selected, right? So these are the field variables. They are the primary variables what we have discussed. These are the steps, as I have said, to solve the CFD problem. You have to discretize the continuum. That means you have to divide the whole domain into number of segments. You have to solve the strong form of equation to weak form of equation. Weak form equations to you have to make the elemental stiffness matrix. You have to assemble all the matrix together and make the global stiffness matrix, apply the boundary conditions, and you'll be go with the solving the equations. Once you solve that equations, you'll be able to find the secondary variables. The secondary variables are the ones which are related to the primary variables. राइट सपोज आपको वेलोसिटी ऑफ प्रेशर मिल गया तो उसके बाद उसके ऊपर से आपको क्या चाहिए सच काइंड ऑफ थिंग्स यू कुड मैनेज विद द सेकेंडरी वेरिएबल्स. So if in two-dimensional problem, if we want to find the finite element implementations, then our aim is to go for Navier-Stokes equations, and we are going to consider that my flow is the steady one, incompressible, definitely, because we are talking about the liquids right now. I'm considering the triangular element over here, and my primary variables are the velocities and the pressure, right? In this particular condition, this is my Navier-Stokes equation. That would be in the variation in x direction. This is my variation in y direction. This is the ultimate equation where u and v are the velocities. U is the velocity in x direction, v is the velocity in y direction, rho is the mass density, and p is the pressure. In this particular case, as I have said, if I want to go for higher accuracy, and in moreover in this Navier-Stokes equations, the velocity is going to vary quadratically. So that's why I'm taking the quadratic shape functions for the nodes 1 to 6, whereas I'm taking the linear shape functions for the pressure fields, and that are velocities. These are the velocity shape functions, these are the pressure shape functions, and these are the field variables, that is pressure, that is the velocity. These are the two velocity in x direction, velocity in y direction, and pressure. That means these three things that I want to find from that equation, right? So if I am going to apply such kind of things, let's say on this one octagonal body. Now in this octagonal body, you could see that I have selected the finer mesh over here surround this particular body, and the coarser mesh on this particular element. So when wind is blowing from this particular directions, you could see the variation on the velocity, how it goes. See, this is the blue color which shows the minimum velocity. You could see that there is a, when it is having a very high velocity on this domain. It is the velocity suddenly getting reduced when it is going to stuck over here. After stucking here, it is going to move something like this. At this particular portion only, my velocity is very less, and beyond that points my velocity is getting increased. This is the diagram for the pressure. Pressure is not exactly similar to work as the velocity works. This is the pressure diagram, right? If I want to find such kind of scenarios, let's say for the other two buildings available I have, and this building I want to construct new, and wind is blowing on this particular from this particular direction. I have the shape functions with me. I have my Navier-Stokes equation. I have the solution of Navier-Stokes equation. I have to just put my conditions on this particular field over there in that equation, and I'll be on where how much amount of pressure or velocity is going to be existing on this particular building. So in this particular case, as I have said that we have to consider the boundary layer theories, I have considered the walls over here, which has a zero velocities and pressure. My wind is blowing in this direction. This is my scenario. This is how I matched it. And this is the boundaries which I have applied. After that, if you could see the velocity which is blowing on this particular field would be in tremendous manner. That is, the velocity was very high in this particular region. Then when it is going to enter in between this particular region, it is very high. But after that, in this particular region, it is going to increase and it would be very high when it is tucked over here. You could see this particular thing. If you have not considered this particular effect, this particular building is constantly under a high velocity region in this era, right? Similarly, these are the velocity in form of vectors. Similarly, you could find the pressure even. Here the pressure is very low as the wind is dispersed into the atmosphere. But this is the region where the very high pressure is going to be exerted. So while you are designing this particular building, if you are interested in that case, beforehand, you have to go for CFD analysis for the stability of such kind of structures, right? So this is about how CFD works, how it is implemented. Now I'm going to discuss about the few things related to environmental engineering. As we have discussed, there are so many issues in environmental engineering to run the effective plants, as well as for the wastewater samples or air samples, where you have to constantly collect the samples. You have to change the dosing as the flow of water is going to change, as per the quality is changed. It can be the quality can be changed, quantity can be changed. So in each and every time, you cannot go for optimizing the dose and everything. You cannot go for designing the newer treatment plant or something. So in such cases, how the CFD would help you, that we are going to see in case of water treatment, air quality, and the solid one. This is the continuous flow reactor, the generally considered to be a CFSTR, that continuously stirred flow reactor systems, in which we are planning to add the coagulants. When we are adding the coagulants into the systems, our main aim is the coagulants to mix into the tank properly. If it is not mixed, the lumps are created. If lumps are created, they are useless. They are adding the load on the wastewater systems, right? If they are adding properly, then they are going to mix with the positive and attraction getting done. So at which point I have to add the coagulants? What should be the angle of nozzle, at which point I have to add? What should be the speed of the turret? At up to which point I have to check the residence time, because residence time is the one important parameter when I'm going to design the mixing unit. If I'm not giving them a proper time, the flocks are not getting formed, and the additionally chemical to the system will add the load, right? So such kind of mixing effect can be visualized with help of computational fluid dynamics. In this particular conditions, generally the Navier-Stokes equations advanced version, that is Reynolds Navier-Stokes equation, or considered to be as a Reynolds average Navier-Stokes equation, commonly known as RANS equation, is generally used. If I have a plug flow reactor, in this plug flow reactor also, I'm going to add the chemicals as a disinfectant or as a coagulant. And I want to check that at which kind of a baffle, what would be the velocity, at which velocity my coagulants are getting mixed properly. right? How the baffle is going to work, what should be the size of the baffle, what should be the position of the baffle, so that the things are getting properly mixed with the systems, right? So this kind of variations are going to be done because of the velocity. This kind of velocity baffles or velocity profiles are getting created with the help of computational fluid dynamics. This problem was solved under the ComSolve physics. There was another commercial software which is available in the market, and that will help you to solve the multiphysics problems. As I have discussed, this multiphysics problems can be solved by the FEM methods. The ComSol is one of the software which is going to be used. So in case of settling chambers, or either that could be a primary settling chamber or a secondary settling tank, where coagulation process or after a bioflux which are generated, if I want to design them in a proper manner, then what should be the size of the chamber, what should be the detention time, what should be the mixing efficiency, what should be the positions of the baffles, what should be the dosage of the coagulant. Such kind of variations are multiple variables, even it can be incorporated in the same time at the same point with the help of computational fluid dynamics. Such kind of things are going to be generally carried out with the Reynolds-Navier-Stokes equations are going to be used. Commercial softwares are available which are the giving you the solution of the RANS equation. ANSYS, Fluent, CFX, COMSOL are very effective for this kind of solving the problems. If we have the bioreactors where the biological sludge are getting formed, in that biological sludge which is going to be present, how the bioflux are generated, what should be the time for which the bioflux should be the effective manner, what should be the active sludge, what should be the recirculation ratio in case of active sludge is present. Such kind of solid suspension or biological problems are getting viewed by the bacterial transport equations. Bacterial transport equations, even you could find the BOD degradation systems equations are available. So such kind of equations, if you are going to find, and they are available, and you could find in advanced environmental engineering books with the biological treatment sections, you will find such kind of equations, right? So this kind of views could be easily captured by the computational fluid dynamics. If you have a pipeline flow, as we know that pipeline flow is there from through which we are getting the drinking water, and we are adding the disinfection into that water, right? What should be the at what time, up to which time that disinfection would be present into the water. If you want to see that, in that particular case, we have to go through this particular CFD analysis. In that case, disinfection treatments can be advanced by using the ultraviolet lights. If you are using the UV lights into the systems, in that case, the amount of UV lights, what should be the dose, how the particles are getting tracked at each and every. This is my line of flow at up. Now in this particular section, what should be the amount of disinfectant present, or on this particular section, this is a Eulerian approach. If you are going to follow the Lagrangian approach, in that case, we have to trace the element, right? So in this particular things, how the things are getting tracked, how the things are going to be formed, if the scales are getting formed in the boundaries of the boilers or a vessels or a pipeline flow, in that case, that kind of things could be easily seen through this particular CFD analysis, right? Uh, Generally, for the disinfection purpose, the ozone is also going to be added as a type of oxidation process, right? That it will be the advanced oxidation. In that advanced oxidation processes also, you could find the optimize the dose, or such kind of things can be done with the help of CFD analysis. Generally, in this particular cases, the Reynolds stress transport model is going to be used with the combination of a very famous K epsilon and K omega models. These are the models which are fluently available in the ANSYS, and this kind of profiles are getting generated through that. if you have, if you want to see the dispersion of pollutants in the river flow, as I said, if I want to check the oil spillage in the water, or I want to find that up to which, at which manner my impurities like COD or a BOD, chemical oxygen demand, biological oxygen demand, how they are going to vary, or how they are going to change with respect to time or with respect to space, how they are going to degrade. Such kind of things are available mathematically, right? That my rate of change of COD with respect to time, if I want to find it with the differential equation, I have to just solve the differential equation and I have to code them if it is not readily available in the software. So such kind of things can be easily predicted, or in case of when your flow is changed, when your velocity is going to be changed, or when in case of your impurities are going to be suddenly increase, in case of let's say a monsoon season where we find that so many number of quantity of and quality of wastewater is getting increased. So in such cases, this CFD analysis will be the blessings, right? In such cases where we want to find the impurities in with respect to time, how they are going to change, such kind of things can be measured with the general advection and diffusion equations, and that could be even used by finite difference method, finite element method. Because in if you are finding for the river problem, the geometry will be the simple one. In the simple one geometry, you can definitely go with the finite difference scheme. Even if we are interested in the air pollution issues, in that air pollution, we could see the different vehicles having the different geometry. In that geometry, the exhaust over here, it is going to mixed with the atmospheric air at what level, right? So that here you could see the vortices are created, you could see that eddies are generated, right? So in this different conditions, how the pollutants are mixed with your atmospheric air, such kind of pollution dispersions on the buildings, on the surfaces, from the vehicles, such kind of things are also getting going to be found by the mass transport equations. This mass transport equations are going to be mainly depends on the wind velocity, wind's direction, and the smoke dispersions. All other parameters are combined together will make the mass transport equation, which having some diffusion parameters are also available. And that is how we are going to solve the pollution which is based on the air. If we have a stack in these three different figures, you could see the stack pattern is different, right? Here it is going to moving upwards. Here it is going to moving on the sides, right? Some portion moving upward, some portion moving sides. This is just a little bit moving above, and then it is going to be dispersed on the side. In such conditions, if you have industry, if you are living by nearest to industrial area, or the persons who are working with this particular industries, in that case, at what efficiency the smokes are going to be, what are the chances of getting those pollutants in the inhalation for that particular humankind? In that case, we have to analyze this particular dispersion pattern, and that dispersion pattern can be, or dispersion pattern or a mixing pattern can be analyzed with the computational fluid dynamics. In this computational fluid dynamics, you could assume, or you could find the height of the chimneys, you could take the wind directions, wind speed, wind velocities, all that primary things that you have to find through your Navier-Stokes equation. Then you have to add the boundary conditions and the secondary parameters as you need to go for this transport equations. So once you are going to apply that transport equations over here, you'll be able to find what would be the dispersion rate or a dilution rate with the atmosphere, or up to which height it is going to mix with the atmosphere, how it is going to mixed in the space atmosphere, even that could be measured or analyzed with the computational fluid dynamics. If we are talking about the solid waste, when we are dumping it, the liquid portion is going to be squeezed and it is going to be collected separately, which is generally known as the leachate. That leachate generations are also getting underground flow, and they are mixed with the groundwater. So to avoid that confusions, if we are going to if we are going to analyze that leachate, and if we are going to apply the COD predictions for that particular leachate dispersion, that also going to help and saving our groundwater source. So that is all. This is the closure comments, that if we are interested in natural resources by saving them, we have to adopt the proper treatment. For adopting the proper treatment and to run them effectively, we have to go for computational approach, which in which the CFD will be the prominent solution. That would be the easy, quick, and appropriate solutions. And for basically the problems which are the time consuming, right? It is going to incorporate in multiple influencing parameters, where if I want to find that I have so many parameters which are affecting my system, and if I want to implement that all together in a single phenomenon, that would be helping with the computational fluid dynamics. Uh, Thank you so much, all of you, for patiently listening to me. And now I'm ready for the questions. If you have anything to ask, please ask me.
Thank you, Monica ma'am, for elaborating the incorporation of computational fluid dynamics in the field of environmental engineering. The forum is open for questions. If anyone want to ask questions, please ask. Are there any questions or discussions anyone would like to have? That also we can do.
If you have problems in future also, when you are working with some problems, and if you have some kind of issues, you can find my email IDs, and everything will be available on the university website. So you can contact me anywhere. I am available via mail and the telephonic conversations too.
Okay, so if there are no questions, then we shall end this session today. A feedback form will be shared to you for today's session, which is an attendance form also. So I request all the participants to kindly please fill up the feedback form. And we will meet tomorrow again for such another interesting topic at 2:30 p.m. sharp. Thank you all for joining us today. Have a very wonderful and pleasant evening.
Bye, guys.
Bye, everyone.
Bye, ma'am.